First then, yes, to express thanks to Christina Verkulich. Many of you have emailed Christina. Thank you very much to Christina for setting up this meeting and for all the hard work that she does in coordinating everything to do with the Railway Challenge. So just a few words of introduction for me. Could we go on to the next slide, please, Christina? Thank you. So this is the agenda. So just a few words of introduction from me, and then you'll be hearing from different members of our organising committee from different parts of the Railway Challenge structure. There'll be an overview of the Railway Challenge for 2021, an overview of the design process, some guidance and suggestions and tips on things you should be doing and shouldn't be doing. Then we've got a presentation on traction of electrical systems, something from the judges that will be useful for you to hear, I think. And then finally, there'll be a question and answer session. We need to try and conclude everything within the hour that we have. So if you have questions, it would be very useful if you could put those into the chat as we go along, and then we'll address those questions at the end, and we'll let you come back with any sort of other additional questions if you want to. Okay, if we could have that, thank you. So just perhaps to set the scene, really, I think most of you know most of what's on here, but basically it's an annual competition. It's organised by the Railway Division of the Institution of Mechanical Engineers. We're a very active division within the IMechE. I think most of you are now members of the IMechE, so please do get involved not only with the institution but also with the Railway Division. We'll be very happy to talk to you about that afterwards. The competition is for teams of either engineering students studying at, well, we've said our UK university on there. That's probably out of date, really, because we have teams from universities around the world now, which is great. And in fact, the winner from last year was not a UK university. More about that later. Or not only teams from universities, but also graduates or apprentices working in industry. So we have many industry teams entering as well. And the idea, as hopefully you know by now, is that you compete with each other to design and manufacture a miniature gauge, that's 10¼ inch gauge locomotive, in accordance with a set of rules and a technical specification which has been published and we'll be explaining a bit more about. We're in our 10th year now. The 2021 event is planned for June the 24th to the 27th. We're very much hoping that will go ahead. Everything's planned around it going ahead. Obviously, if things change due to the pandemic getting worse or whatever, then we'll have to inform you. But our current plan, we're very optimistic. We will be going ahead June the 24th to the 27th. We also have an event in February. A little bit more about that later. On the next slide, please. Thank you. Just a little bit of an overview about the 2021 event and some things that you need to know about. There are several documents that you need to be aware of. First, perhaps most important, are the rules. The rules are set each year by a committee. They change a little bit each year, and they're published each year. That committee is led by Tim Fairbrother. And then we have a technical specification, a separate document. It's a common way of doing big engineering projects is to set out a technical specification for the project. That technical specification is led by Tim Poole, others supporting. Then there are other things as well. There are other diagrams which you probably will be familiar with now, all on the website, and other supporting material. And I just wanted to remind you that we have a question and answer facility. In the way of all sort of big projects like this and tenders, to be fair, any question that you submit is considered by the committee or a subgroup of the committee. We aim to answer you very quickly, but the question and the answer is circulated to all the other teams as well. So we want to follow that formal procedure. If you have a question, then please send it to Christina. Scrutineering takes place at the beginning of the Railway Challenge event, and we have a team of scrutineers who are led by Tim Poole again. I just wanted to explain the difference between the scrutineering and the judging, and one of the differences is that the scrutineers are made up by people who are affiliated with teams. So if your team wants to supply somebody to support the scrutineering, they can do. Contact Tim Poole. We'll probably have them in place for this time, but in future we can certainly add them. The judging, on the other hand, is carried out by people who are independent of the teams. So judges don't have affiliations to the teams. If they have a distant affiliation, like they may be graduated from the same university or something like that, then they fill out a sort of declaration to show that there's no conflict between. And the judges are led by Bill Reeve, who's our head judge, and Malcolm Dobell, who you will hear from later today. Next one, please, Christina. Okay, so I'm now going to hand over to Tim Poole, and Tim Poole will talk to you about the an overview of the design process. Thank you, Tim.
Thank you, Simon. Welcome, good morning. Hopefully you can all hear me. My name's Tim Poole, and I wrote the tech spec, or led the writing of it. First, can we go back? Oh, we're shooting. Right. Thank you. And basically, this tech spec is based on a real tech spec. So obviously, the first thing we aim to do on the Railway Challenge is to make sure that this is something that represents what you would find in real life. This is obviously supposed to be very much part of your development. So the tech spec, the whole competition is based on real life. The other two things, of course, we have to do are safety and also level playing field. So those are the three priorities. So we make it so it is part of your development, it's utterly realistic, and it's safe, and there is a level playing field. And that's what we try and do each year with the challenge. In terms of making it realistic, the key thing we do is make it like a real railway specification would be, railway vehicle specification would be. And nowadays, the trend has been for a decade or two to make it a performance spec, i.e. we do not specify how you do anything, we specify what the performance of the vehicle has to be without saying how that has to be achieved. This, of course, does give us lots of scope for innovation. It gives you the ability to do things however you want, design the locomotive almost any way you can within these limits, and that hopefully will make it much more interesting for you. This is very much how the spec was written, which this spec is based on. The real life spec was for some works locomotives, and this is very much a cut down version of that. And this was exactly how that was as well. So performance specifications is what you will be coming across as you progress, hopefully, through the railway world. The only thing where the real life loco did actually have one specific piece of design in it, which was quite a major clause. It said the locomotive will be diesel hydraulic. That, of course, has been taken out of this spec. You don't have to do that at all. That was the only thing which was written in there. And that is because electrical design is much harder than you think. And we're going to focus on that in a minute. So there are lots of proven mechanical components, and we didn't have time to go through the electrical design assurance processes and EMC, which we will also come to. So I'll start off by looking at some of the pitfalls that you may well come to. And this is part of our level playing field. We do want new teams to feel they're not at a huge disadvantage. So what we do on these slides, and these are available on the website, is to show you some of the really common pitfalls previous teams have had to give new teams the confidence that you're not hopelessly disadvantaged by being new, because you really aren't. And as Simon will testify, many times to prove we've got this right, it has been new teams that win. And I'll come to exactly why that sometimes is at a later slide. In the early years, one of the biggest problems we had was with teams who correctly identified chain drives as being relatively efficient, but the chains kept flying off, breaking, etc., etc. So the first tip I would say is have a look at motorbikes, how they do chain drives. Please, if you are going to use a chain drive, pivot the suspension from where you drive, as in the diagram here. In other words, if you have the axle, or whatever it is, the shaft that's driven completely independent of the shaft that's driving, the chain will either slip or snap. Look at how motorbikes do it. Pivot the moving axle from the driven axle point, as in the diagram, or you will break or slip the chain. So please bear in mind, it is a tempting drive to use. It is a good drive to use. Please do remember this tip. There is one way around it: idler gears, idlers, tensions, if you like, tension wheels, but that just adds a degree of complexity. Have a look at motorbikes, how they do it. Next slide, please. Secondly, the other thing, make sure that when you drive chain wheels, the shaft can't move sideways either, because the moment you move a driven shaft sideways, longitudinally, the chain will fly off. So make sure whatever suspension systems you have perfect alignment, and it stays perfectly aligned along the length of the axle as well. It can't slide sideways. That, of course, is exactly how you change gears on a push bike. You really do need to make sure there's no longitudinal movement of the axle. Thank you. Next slide, please. The next thing is push connectors. This again was one team had a major failure of their locomotive, where a pipe fell off the back of the horn, believe it or not. That, of course, that horn was being fed off the main air main running down the train, which of course is also what powers the brakes. And the locomotive correctly had a system that if you lost the air pressure, all the brakes went on. So literally, the connector flying off the back of the horn brought the entire thing to a very severe and terminal halt. Basically, the pipe was held onto the back of the horn just because with a rubber normal push fit connector, which in normal life would be fine. Locomotives are a very harsh vibration environment. Don't rely on push connectors. In fact, don't generally rely on anything where it is a single connection. In other words, with this push fit, there should have been a Jubilee clip round it as well. Not necessarily in normal environments. On a train, you need to do this. If you're going to put circuit boards onto a backplane, don't rely on the friction of the circuit board in a backplane. That may be perfectly okay for a computer at home. It certainly is not on a train. It will fall out. So really look at every critical connection you make sure it's held in at least twice. We'll come to some more slides. Thank you, Christine. Next slide. And so there we are, another example. There's a push fit of a PCB going into a backplane. If you do have such a device, remember that will fall out as quick as you put it in on a train. Trains have steel wheels running along steel rails, running along rail joints. They are being hit roughly every 10 seconds with a hammer. That's how you have to consider a locomotive. If you push this into a circuit, into a backplane, it will come out as quick as you push it in within about 50 meters. Please double secure every joint. Thank you, Christina. Next slide. And that, of course, is the same with nuts and bolts. Do not just use nuts and bolts anywhere on the locomotive at all. Please think of some way of locking them in. You can use any one of these systems that I've put on this diagram here, but please lock everything in. This is a very nasty vibration environment, a locomotive, and any nut and bolt that is not fixed twice, if you like, locked in some way, will come undone. Thank you. Next slide, please. The next thing is, and this is where we come to what we found was quite surprising on the challenge, which was it wasn't always the old teams that won, which was a slight mystery to start with, and then we realized what was going on. If you have last year's locomotive and they have not done the wiring neatly, they have not logged the change to the wiring, they have not done proper wiring looms, proper diagrams, not put cable labels on, what happens is the team who then inherits that locomotive the next year, when it doesn't work, and that is almost 100%, they will have no chance of mending it whatsoever because they have not got any diagrams, any wiring labeling, and they will have no clue as to how to mend what is not functioning. More for the sake of the next year's team, but even for the sake of yourselves, when it doesn't work in the field, when something goes wrong, please really do think about how a professional locomotive would be built. And it would be done with neat wiring looms, every cable labeled, everything written up on a schematic diagram, so that when things don't work, when things go wrong, you stand a chance of getting it mended. The number of times we see teams, sort of 8, 10, 12 hours working all night on locomotives, trying to work out why it doesn't work, what's connected to what. please put a bit of effort into the wiring and making it neat. Be really neat and tidy. Yes, electrics do work if you just run millions of separate cables unlabeled from point to point. It will work on day one, but you try mending it on day two, not a chance. So please, so your locomotive works. We so hate to see you all at the site with a locomotive you spent months and months working on, not functioning, not able to enter the competition because you can't mend something that's gone wrong. It's so disappointing because we know how much effort and enthusiasm we put in, and we do love all the locomotives to work, which is why we have these hints and tips pages. So please really think about getting your wiring neat. It's not an unnecessary annual thing to do. It just gives you a chance this year and someone a chance next year of getting it mended when things go wrong. Thank you. Next slide, please. We now come to the subject of EMC. I'll be talking a little bit about this. My colleague will be talking a little bit about this. This is a really big subject. This is a thing that puts the fear of God into all of us, as well as neat wiring. And I should point out, during the tendering process of the real locomotive, which this spec is based on, we more or less rejected a contractor because their wiring looked like spaghetti. We thought, this is not professionally built, this is not mendable. And so not only do you have to get the wiring neat, you have to think about EMC as well. In real life, this is an absolute showstopper. This takes an awful lot of time to get assurance for rolling stock on Britain's railways, partly because, of course, you must not interfere with signalling, but also you will bring unreliability on yourselves. This particular drawing here shows an unlikely arrangement of half the locomotive control at one end, half the other end, running through this odd device in the middle with sparks. That's an exaggerated issue. That would be very unlikely to work. It would be very unlikely any of those low voltage, low amp signals going through that device in the middle would actually function at all. That is obviously an exaggeration, but there are a lot of devices producing all kinds of electromagnetic fields on your locomotives. The transformers, the generators, the motors, and probably the traction control system yourselves. So be really careful when you're thinking about how you're routing wiring, which wires you need to shield, etc. We'll come to that in more detail later, but be really careful because often faults that appear to be totally inexplicable. Let me go back 2 slides. We've jumped. The next slide, please. Thank you. So here's some quick hints and tips provided by one of my colleagues. Make sure you have isolated power supplies to power the control electronics. Electrically isolate all control inputs, outputs. Why not use opto-isolators? That's a very good way of doing it. Keep the control wire neat and away from the noise sources, unlike that diagram you just saw. Use twisted pairs and screen cables. Think about if you can't avoid it or you're worried, screen the cables. Have a common chassis earth. Make sure that everything goes with a single connection to the ground, not 2 connections, or it'll build up earth loops. Avoid circulating screen currents in the control electronics. Have a common connection point for screen connections. Again, back to that single earthing point. Obviously, if you can, put stuff into earthed metal enclosures rather than plastic enclosures. That will help you as well. There's just a few hints and tips. So really think about EMC because the trouble with an EMC fault, there is not an obvious fault. It's not something you can see. You can't work out why the signal isn't going from A to B. They appear to both be connected at both ends. These are very difficult faults to isolate. So really think about EMC. Next slide, please. Also bear in mind when you're doing your design, many of you will use generators. Remember that the signal coming out of a generator is not the neat sine wave that you were imagining it might be. It will be a very spiky, nasty thing. So make sure you think about either overrating your electronics by a huge amount or having some sort of spike blockage system. If you have all your components rated exactly the amps you think they're going to be, because that's the cheapest one to buy, it will fail immediately because there are very few parts of the traction system on a railway locomotive that actually have a neat sine wave or a neat straight line that you think they do. Really overrate your electronics and really, and my colleague will come to this further, and really make sure you have all kinds of suppression systems. We have so many teams over the last 8 or 9 years who have fried their electrics because what theoretically is needed is not what actually happened to the wiring. So really think about this. Thank you. Next slide, please. The same thing. It's not just the output; it's the motors themselves. You do some neat calculations, and you decide this is the amps that this motor should take as it goes up the hill and then runs along the level and finally comes to a halt. The actual supply, the actual current it will take will look something like this, as all kinds of things happen on the way. It'll hit a rail joint, which will almost sort of stop the wheels in their tracks. The motor will cause a huge spike. There'll be phasing issues. Don't even talk about AC motors, which will cause terrible pure mass to happen. And of course, at the end, if you brake, motors are generators. So what you think will be a positive current going into the motor, of course, all motors are generators. It will just generate electricity back the other way. And if you've got components that don't like that, because you assume which way the current was going, they will be fried. So be really careful to make sure you have a huge overrating, huge spike suppression, and huge tolerance on your traction components. Because it's been really sad to see teams not being able to run their locomotives because of burnt out electrics. Thank you. Next slide, please. And finally, the loading gauge. That diagram hasn't come out brilliantly in PowerPoint. Remember, all we can do in the specifications, and this is the same for any railway on any railway locomotive, no railway can tell a locomotive builder how big the locomotive should be, because all they can do is say how big the railway is. How big the locomotive should be depends on how soft you make the suspension, the 6 degrees of freedom that your locomotive will have, and also the dimensions, in particular, what's called the center throw and the end throw. So in other words, what you are doing is designing a locomotive that when it moves around with its 6 degrees of freedom, and when it goes around corners, up vertical and horizontal with the end throw and center throw, it fits in the kinematic envelope you can see on this diagram. The locomotive itself will be notably smaller than this diagram because it does move around, it does have end throw, and it does have center throw. And you'll need to convince the design judges, led by Malcolm, that you have duly considered these other factors. This diagram you see on the website, this is not how big the train should be. This is the size it has to fit in. The locomotive will be notably smaller. We can't say how much smaller. It depends how much end throw, center throw movement you have. Thank you. Next slide. So I'm now going to hand over to Stuart, who is an expert at electrical design, who will try and steer you through the tricky subject of the traction electrics in more detail. Thank you very much for listening.
Thank you, Tim, and good afternoon, everybody. So I'm going to tell you a little bit about how much power we need to create in order to move our trains, or your trains. So next slide, please. The physics of traction is really remarkably easy. You know, it's basically Newton's law, F equals ma, and the forces that are working on your locomotive and coaches, if there's a difference between the forces, then the train will accelerate. So the traction force is what you apply to the wheels and to the rail, and then there's a resistance to motion and or obviously gradient slopes. It turns out that actually the gradient slope is the most significant thing you need to worry about for this challenge. But before I talk about that, when we normally do this, we're normally face to face, and it's quite hard not being face to face. But I always ask a question, and has anybody in the audience ever pushed a train? And a lot of people go, how that's not possible. So if any of you have pushed a train, Can you just add in, say yes in the comments? I want to see how many have. And I know there are definitely people in the committee that have pushed trains. I can guarantee it. So I suspect Malcolm might have done, and maybe Tim. I don't know if you're allowed to do it, but yep. So I've got one yes already. So you can actually push a rail vehicle. Oh, there's loads of you. Excellent. You can push a rail vehicle because it's got a very, very low low rolling resistance. So when it's on the flat, you can move a coach with just a few people just pushing on it, and that coach may weigh 20-30 tons or something. So it's really remarkable. So when trains are on the flat, it's quite easy to get them going and to keep them going. But when the train's going up a hill, then you need the power. And it turns out for the power, God, everyone's moved a train. Brilliant. don't push it over the edge of a downgrade. Good idea, that one. Yeah. So yeah. When you're going to work out the power required, you need to really focus in on the slope part of the track at Stapleford. So next slide, please. These are the sort of things you need to worry about. Is what the mass of the vehicle, what's the required acceleration, maximum slope, available adhesion, and what is the speed that you require when you're going up the maximum slope. So you can use all them and do some simple multiplications and basically find out the force, the gravity force pulling you down the slope, and then multiply that by the speed, and then you get the power that's required to go up the hill. It's as simple as that. So just doing simple calculations can give you an amount of power. One thing I'll come on to in a bit, you need to match this power requirement with the motor power requirements. And what you'll find is motors, you can get very high powered motors, but they only produce their maximum power when they're spinning at their maximum speed. So you need to bear that in mind, because you need to have a gearbox which might be going from a very high ratio down to something very low, and that often is difficult. So what we found is many teams end up overrating their motors based on the torque that's required rather than the power. So you might have a very powerful motor, but you're not using the full power capability of it. Next slide, please. In the power calculations, we need to worry about losses as well. So you obviously have energy coming into your vehicle with primary energy, and some of it's lost in its trip to the wheels, and obviously you get some back through regeneration. So you need to take into account all of these losses, otherwise you'll end up with a underspecified system. So next slide, please. So these are the main equations that you need. Actually, the most important one is that third one. Power is force times velocity, and you can get the force either from the acceleration that you require up to a certain speed, or the gravity force that you require. Now, in Stapleford, the gravity force is the thing that's going to dominate this. So when you work out for your mass of your train going up the slope, and I can't remember exactly how much the slope was, maybe someone can put it in the comments, but that can give you your sine alpha, and multiply it by gravity, which for us engineers 10 is good enough, and the mass of the vehicle, and you'll get the force pulling the train back down the slope. Then you multiply that by the speed in meters per second, and you will get the power that's required, mechanical power that's required to move it's about 2% or something, right? Yeah, that'll be the power required to go up the hill, and you'll need to then size everything based on that fundamental power requirements at the wheels. Next slide, please. Got some pictures now. So that's an American train, just to show you some pictures. I'm not sure why, but we like trains, don't we? That's a very attractive Series 500 Shinkansen in Japan. And next slide, please. That's a very attractive pacer running up somewhere up the north near Simon. I think he probably travels on that every day. Next slide, please. And that's one of our newer trains, Tachi train running. I think that's a Great Western train, probably before it got painted. Next one, please. And this train, I always think of this as one of our new trains. And this train is probably about the same age as many of you. It's 20 years old now. So just think when you get to my age, they might be thinking about retiring these trains. So it could well be around for another 20 years, running up and down West Coast Main Line. So trains have a very long life. And then this slide here is our University of Birmingham entry from a number of years ago, showing an example of one of the locomotives. Next slide, please. I just want to talk about some of the motors that you're gonna potentially buy. There's kind of three options really. There's one which is called an induction motor, which is an AC alternating current motor. One which is a DC brushed, and then the other which is DC brushless, which is actually a bit like an induction motor. To some extent, but it's a bit of a hybrid between the two. You need to think about which one you want to use. If you're really not sure, then the easiest one to use is probably a DC brushed motor. But if you've got good power electronics people and motors people on your team, then maybe go for something more complicated like an induction one. Next slide, please. Now, inside motors are magnets, and nobody understands magnetism, but this is a picture of a north and south pole from a bar magnet. And as you know from playing with magnets as a kid, you will know that they exert a force, and you can make things move with them. And that's what we harness inside a motor, is the ability to move magnetic fields and create torques within the motor itself. Next slide, please. In a typical motor, you've got the outside bit of it, which we call the stator, the inside bit, which is the rotor, which rotates, and then your end housings. Next slide, please. And this is just an example. You will also find inside motors windings. So A and A dash here are representing a loop of wire which runs around the machine. It runs along one end and then comes out the other end and then back along the opposite side of the stator. And that shoving current through that will create a magnetic field. And by carefully managing that magnetic field, we can create a torque and get the stator to rotate. So next slide, please. So inside your little motor, you actually get field lines which look something like this, and it's similar whether it's an AC or DC one. So there's actually a really, really strong magnetic field inside your machines, and most of that stays inside the machine. Very little of it escapes. But just reflecting on some of Tim's comments, he said about electromagnetic interference. Your motors and stuff will generate sort of stray magnetic fields. So if you put like sensitive cables right next to motors, then you expect to get some problems of electromagnetic induction into your control cables. You just need to be wary of that. So next slide, please. This shows a picture of a three-phase supply system. So if you're going to go and use an AC motor, you need to generate three phases on board your train. So if you've got confident electrical engineers within your team, then this would be a very, very good way of doing it. It is in fact the way most trains are driven. Most modern trains have AC traction motors, and they generate a voltage like this on board the train and send it to the motors. And in order to change the speed of the motors, you need to be able to change the frequency of this supply. So it's got to be a variable frequency supply. Next slide, please. This is a picture of a motor taken to bits, showing you all the bits of it. And we'll just go quickly on here. Next slide as well. A DC motor is much simpler. It doesn't have a rotating magnetic field, and it only has 2 terminals for the armature, so it's a lot simpler. Next slide, please. So with a DC motor, we only need to control the voltage that we give the motor and monitor the current. We control the current that's going into the motor by varying the voltage. So if you have a DC motor, you need a variable voltage DC source in order to drive the motor. And next slide, be the final motor one. This is a brushless DC machine. So these are the common kind of motors that you get for running drones and remote control cars and stuff like that. And you can get some really high power ones now, and they're quite easy to control. So and they're very efficient and high. They're really good things to have a go at. So think about them too. Next slide, please. You can get loads of stuff online. This company, Lynch Motors, has been commonly used by a number of teams. So have a look at them, and you can get controllers like this. Robotech make controllers for all sorts of different types of motors. So there's lots of information on the web. Next slide, please. So next things you need to do is to work out how much power you need, the energy consumption, and how fast you need to go, and so on. Next slide, please. Things you need to start thinking about buying are the motors, motor controller, and something to control the motor controller. So your motor controller will need an input for itself too. And next slide, please. Problems. We already mentioned this. Power circuits are high power, high current, high voltage. If you've got electronics nearby that, they could get interfered with. So most students will blow up motor controllers and electronics during the course of building this. We also need to think about what happens with e-stops as well. What happens when you hit the e-stop in terms of shutting down the train. Next slide, please. More things to worry about. These that we've already mentioned. There's cable IDs, crimping, and terminals. So if you put your cable in and you screw something down onto it, what will happen is that will come undone. So crimping is really, 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 really important, and how to attach it to stuff. Railway does this very, very well. Normally, if you're using chock blocks for anything, they will come undone and something won't work. So no, they're a big no-no. Cable IDs are really important. So the team coming after you can fault find, and also you can fault find a lot easier. And then thinking about earth in your train, what does that mean? Earth in your train, that's a big issue, particularly when you think your earth cables might need to carry fault currents. Next, please. So yeah, just a final point about people inside your teams. And I've worked in lots of big teams. You have different types of people: organized people, unorganized, extroverts, introverts, team leaders, followers, and worriers. Ideally, a team's got all of them in it. You need to find out whose role is who's doing what, and then work within the team to get the best out of each of you. And then I've got a final slide, and then I want my colleague Felix to say a few words. So can you show the next slide? This is the diagram on the right is what your locomotive should look like, not the one on the left. Okay, so the one on the left is a complete nightmare. So Felix, can you say something quickly about the supercapacitor voltage and a bit about wiring, if you want? Thank you.
Yes, I think.
And then afterwards, Felix, you can hand straight over to Malcolm. So thank you very much, everyone.
Thank you very much, Stuart.
Thanks, Stuart.
Can I keep that slide on, Stuart, for a second? The left-hand side is, as Stuart says, an absolute nightmare of a wiring system, because none of the wires are labeled apart from the 2 or 3 which have been added late. The one on the right-hand side looks really attractive, but if anything goes wrong and you have to try and take a wire out of this and get the thing back together, it's not easy. So you need to find a good compromise between the 2 options of something which looks really good and something which is easy to fault find. So trunking is a good idea, where you can put the wires in but get it out again. Lots and lots of cable ties is not such a good idea. The other point which Stuart made, and which is a very, very important one, when you do energy recovery, somehow you have to demonstrate to the judge how much energy you have actually recovered during the stopping process, and what you then will be able to use for traveling. When we started this process of this challenge, supercapacitors were very expensive, and people got the smallest one that would do the job. Today, people install huge supercapacitors, and then they are very surprised when nobody can measure anything. So if you get a very big supercapacitor, then your voltage change during braking may be less than
half a volt. And that's difficult to measure, and it's certainly difficult to demonstrate to a judge that you're not cheating. So it's very, very important that you get the right size supercapacitor, which can take all the maximum braking energy you can probably accept, because you know exactly the speed of your train at the point where you start braking, and you know its mass, and you know the mass of the trailer, and that's very important, and the people on it, because that's the mass you are braking, and that gives you a v square mv square over 2, and that's the energy which you need to store in the supercapacitor. Don't go out and buy the biggest one you can afford. Get exactly the right one, but make sure that the voltage is high enough so that you don't blow it up. And from my personal experience, I've been helping people fault find. I've been helping people sort out blown up devices for the past 6 or 7 years. And make sure that when you buy your controllers, you don't buy the one which just does the job. Buy the one which does 1.5 to 2 times the job. But don't go one for big, which is even bigger, because that again causes problems. A lot of the cheap controllers are labeled with a certain wattage, and you have to assume that they can do half of that. And we had a very, very successful team from Poland last year, and they had to buy the cheapest possible controller, which came from a country in the Far East. And it basically, in reality, was rated at about half of what it said on the label. So that is very, very important, that your controller is matched to the motor, and that both are powerful enough to do the job and get you up the hill. Because on the hill, you also have to accelerate. So that's the biggest and most difficult job. I think that's all I'm supposed to say. So. Okay. But if you have got questions about that, then you can email me, and I'll put a link, my email address in the chat. And now hand over to Malcolm.
Yep.
Hello, everybody. I'm talking on behalf of the judges. Bill Reeve is our chief judge, and I assist him, and I judge the design competition, which I do myself. The thing about the judging is we want all the teams to do our best. This isn't something where we want everyone to observe the rules to the absolute minutiae. They might, we will stretch the rules as far as they possibly can be in order to make sure that good ideas are recognised. But if you get things wrong, if you really get things done unsafely, or we make other significant lapses, then there will be penalties, and any persistent or gross safety failure might attract severe sanction. In the worst case, people might get disqualified. Sorry to start on such a negative point, but it's important to get that out of the way. Next slide, please, Christina. Next slide, please, Christina. Thank you. So when I judge the design challenge, all I've got is what you write and any illustrations you provide. I can't see it, I can't touch it, and you should take all the space that's allowed to you to describe it. It really is no accident that teams that score the highest marks generally use all or nearly all of the page count that's allowed. There's a requirement in the tech spec for a compliance matrix, and there's one that's illustrated in the documentation, which gives you the opportunity to say how you have complied with the requirements, and that's useful because it means you can start by saying how you might comply with the requirements when you're starting the design, and then later on say how you have complied with the requirements, which helps me as a judge identify where that description is, and it helps you as contestants to make sure you've actually carried out everything that's required of you. All too often, I find that I'm looking to measure compliance against a certain clause, and find there's absolute silence. So there's something to bear in mind. Secondly, and this might sound obvious, but diagrams need explanation, explanations need diagrams. Safety critical systems need to be clearly explained. And many a time I've found it difficult to work out whether the emergency brake is something where it needs energy to apply the brake, or it needs energy to release the brake. Clearly, it matters which is which. So please make sure you cover that. Next slide, please, Christina. With the innovation challenge, there are 1 or 2 times where people have submitted a learned paper about an innovation which doesn't actually appear on the locomotive at all. And that's not right. The idea is you're supposed to write a learned paper about an innovation that does appear on the locomotive. Now, we've also had 1 or 2 occasions when people have written about an innovation that they were planning to put on the locomotive, and perhaps they ran out of time, or they found it didn't actually work. But if that happens, you need to have a pretty good story so you can convince the judges that your innovation paper is valid. Next slide, please, Christina. The technical poster challenge is something which teams are generally getting done quite well now. It's laid out well in the rules and the tech spec, and above all, it's appreciated by the spectators who can learn more about the designs. Before we did the poster challenge, often the teams have been disturbed by visitors who wanted to know a lot more about the locomotive. They can learn a lot more directly from the posters. And in the business case challenge, where they have to present to a panel of judges, our tip is to have not too many presenters, but also not one presenter. The idea is this is not death by PowerPoint. You can use your poster to amplify with handouts that cover the financial calculations, such as the costs, the benefits, and how capital investment is amortized. This allows for the judges' fading eyesight, because the average age of the judges is well over 60. You will be timed on the business case challenge. Small infringements on time won't be cut off, but might just be penalised. Next slide, please, Christina. Maintainability challenge is one where you're taking out a wheel set, and you're going to have a half-ton locomotive up on jacks of some description, and it will involve people working around and possibly under the loco. There are numerous hazards and risks, and you must make sure you submit your method statement 2 weeks before you arrive at Snappyford, so that the judges have a chance to look at what it is you're planning to do. We will also be observing very carefully that you're all working safely and looking after the safety of yourselves and your colleagues. If you start working grossly unsafely, that's where it might lead to disqualification from this challenge. So put a bit of effort into your method statement, and I'm sure that will go nicely, safely, and efficiently. Next slide, please. Reliability challenge is a bit different. You get awarded points at the beginning of the weekend, and they're yours to lose. One of the things we take account of is a chartered engineer's certificate that there's been prior testing before you arrive on site. And believe it or not, 1 year a team submitted a video of the locomotive moving back and forth by about half a metre or so, which isn't really a satisfactory test by any stretch of the imagination. The reliability challenge runs the whole weekend, not just the Sunday testing, and you get deducted points if the locomotive breaks down, you delay other teams, and so on and so on. But fortunately, you can't go below 0. Next slide, please. Auto stop challenge is a tough one. I don't think any team has yet succeeded in stopping accurately. So bear that in mind, and also bear in mind that even full-size railways don't find accurate stopping easy. We've found that too much braking will stop short, too little braking might overrun, but curiously, a little too much braking might still cause an overrun, contrary to what you might think. And for the ride comfort challenge, don't forget to provide the easily accessible mounting plate for our accelerometer. Next slide, please. The energy challenge, I think Felix has already really covered this quite well. You have to be able to demonstrate to the riding judge how you know that you have only used the energy recovered during the test brake application before you move the train. Teams have been disqualified from this challenge for failing to convince the riding judge, so that's an important thing to bear in mind, and take into account all the things Felix said as well. Won't add any more on that one, so please move on. Next slide, Christina. Traction and noise are straightforward. The traction challenge runs on the up gradient at Stapleford, which we've already said is about 2%, and the noise challenge is run more or less concurrently, and that doesn't seem to give the teams any problems at all. So I think that's about my best last slide, but I'll just make the point that all the judging is based on the real life railway. Tim made the point that specification is based on a real life specification. Judging is not dissimilar to what will be carried out by people judging tenders, assessing design reviews, scrutinizing designs to make sure they comply with standards and regulations, and checking that vehicles perform in accordance with specification. So, and if you've got any queries at any time about judging, don't hesitate to ask. Finally, penalties. Things will go wrong. We will give out penalties if people get things wrong. They're mostly described in the rules. And if you do get penalties, we will seek to advise team leaders individually before we give out the prizes. But if time's tight, we might only talk to people in advance if the scores are very close and the penalties might make a difference. I think that's my lot, Christina. Just move on one slide, will you?
Yeah.
Yeah, that's my lot. So back to Simon. Thank you very much, everybody.
Brilliant. Thank you very much, Malcolm, and also thank you to Tim and Stuart and Felix. So we've got a question and answer session now. I've been looking, I don't think I've seen any questions in the chat. There were a couple of comments when you mentioned that the braking hadn't been accurate, Malcolm, and Arkan pointed out that I think they did get very close, didn't they, last year or the year before? Don't remember the number, but it was millimeters.
I think
okay.
that's fair. Yes. Yep. I forgot that bit.
But then, as there are no questions in the meeting chat, we do have a few minutes. So if anybody would like, if you want to, you can unmute and ask a question if you'd like to. If you say who you are. No, everything must be clear.
I'll take that as you delivered a really, really good presentation and everything is so clear.
Thank you very much. Okay, well, as we mentioned earlier, if anybody does have a question, you're welcome to send it to Christina and it will be circulated to the committee and you'll get a response, but it will be circulated to others. Okay, there is something coming in. I can't see the name, but it's may ask about the different concept between the rolling. Sorry, I'm not just seeing the. There's a couple of questions coming in now. Okay, yeah, I think from the Thai team, isn't it? Difference concept between the rolling resistance and the maximum adhesion available. Tanapon, do you want to clarify that question?
I think I know what the question means, Simon.
Go on then, you answer it please, Tim.
Rolling resistance is basically how hard the train is to push along. So in other words, we roughly assume on real full-size railways that for every ton, it's roughly, you need a 6 kilogram force to make the thing move along. So that's how hard it is to move the train. Adhesion is the coefficient of friction between the wheels and the rails, which could be, let's say, 17% worst case, typically, or less on greasy rails. So that's the actual friction between the wheel and the rail, which is not the same as how hard the train is to push along. You could have virtually 100% adhesion, which would be cogwheels, rack railway, which would still be incredibly easy to push along. So that they're quite different. It's how hard the wheels grip the rails and how hard it is to push along. Think of a rack railway and you'll realise they're completely different things. A rack railway has virtually infinite adhesion, but it has no rolling resistance if it's all nicely oiled.
Okay, thank you very much, Tim. Then there's another question.
Can I say something on that as well?
Yep.
You have to be very careful that you have a decent amount of load on your driving wheels. Mr. Brunel got this completely wrong. He tried to keep the locomotive as light as possible and put all the weight in a tender. So you need to make sure that your driving wheels have got a good percentage of the mass. And I think if you assume an adhesion of about 20%, that's probably taking it fairly high.
Yeah.
Okay, thank you. Then there's another question from Martin Simon about the throw. Basically, in what format would you expect us to prove the centre throw of our locomotive? The actual loading gauge can be proven by a cutout. Tim, I think you did mention that, but do you want to come back on it?
Centre throw, what that means is obviously a very, very long locomotive when it goes round the corner effectively uses a lot more than its nominal size, because obviously the centre of a long vehicle cuts the corner, if you like, and therefore the vehicle has to be much smaller to fit in the same size tunnel. Does that make any sense? Imagine a long articulated trailer on a lorry, the way it cuts the corner because of effectively.
The question is actually how you want them to prove the centre throw of their locomotive.
Well, I think you'll find that what Malcolm will first of all expect is some sort of theoretical or actual measurement of the train movement. Remember the 6 degrees of freedom. Roll, pitch, yaw, long, vertical, horizontal, lateral. So you'll need to show that you have modelled the train suspension, and therefore you have a reasonable idea how much it will move. And then what Malcolm will expect to see is obviously the physical dimensions of the locomotive. That will be the distance between the bogie centres, and the centre throw will come from that compared to the curvature of the railway, what we have specified as the minimum curvature of the railway. So if you imagine you can just draw it on paper if you like, if you don't want to.
So a diagram would be okay then, Tim?
Diagram's absolutely fine, as long as you can convince Malcolm, how much the locomotive will cut the corner as it goes round a corner, and that totally depends on bogie centres and the diameter of the corner.
All right, I think that answers that question. There's another one then on energy challenge from Rob Davison. If we count the watt hours in and count them out again, will this comply with the rules? Okay, this is the energy storage. Is that one for Stuart or Felix?
I'm quite happy to answer that one. You will have to demonstrate that your method of measuring the watt hours is very accurate. So you need to measure the current to a very good standard, and you need to measure the voltage at which that current is being transferred very accurately. So you can't just use an ordinary cheap multimeter or something like that. It is probably the best method, but nobody's done it so far. So please, that could be your big innovation.
Cool. Okay.
Yeah, it's a good idea that, but just one thing is you have to put more watt hours into your battery than you can get out of it, because you need to take into account the losses of changing that electricity into chemical energy and back again. So
okay, you can't assume a perfect battery.
No.
Nor a perfect supercapacitor for that matter.
No, true. Yeah.
I think that's a very big measure. But measuring the voltage on the batteries on its own is not good enough.
Thank you all.
Okay, good. Thank you. Hope that answers your question. Rob, if you want any more detail, then feel free to send it to to Christina for a question and answer session. Okay, we're about at the end of our time. I think we've answered all the questions that have come through, unless there's any other burning question. No, then I think I'd like to again thank everybody. Thank you, Christina, for arranging things. Thank you to Tim and Stuart and Malcolm and Felix for presenting and answering the questions. And thank you very much to everybody for participating. We look forward to seeing you at the Railway Challenge, of course, and at the visit in February, which is on the 3rd of February. Christina will be sending you more details about that, and hopefully social distancing rules and whatever is going on at the time permitting, we will go ahead with that visit. Thank you very much, everybody.